Go.
Welcome to CERN, welcome to Dark Matter Day, a celebration organized around this date, 31st of October, worldwide. We are not celebrating Halloween today, we are celebrating something that is not visible, but its effects are so clearly observable and observed that it must be there. Dark Matter Day this year involves many scientific institutions like CERN, many other labs and scientists who have organized events in 157 countries in spite of the difficulties and mostly online, understandably so. Here at CERN, we have a lineup of a wonderful selection of dark matter hunters, the scientists who every day try to understand and catch dark matter. And they're here to tell you more about these intriguing scientific mysteries, one of the most intriguing scientific mysteries there are around in science today. We've already received from you many, many questions. We're trying to answer them all along and also offline because there are so many. But before we start answering these questions, calling in the scientists, I would like to introduce to you my colleague Achinthya Rao, who has prepared a few tricks for you viewers.
All right, thank you very much, Paula. So thank you for joining us here at CERN today. As Paula said, we're going to spend the next couple of hours taking questions from you and answering them on the subject of dark matter. And the way we're going to take these questions from you is for you to visit a website, enter a code, and then send us your questions. So when you're ready, please visit slido.com, that's slido.com, and enter the code DMD for Dark Matter Day, DMD 2020. And send us your questions. We will have our experts all evening ready to answer your questions. But first, we have a question for you, and I'm going to create a poll right now. So we know from observations of the universe that there's a lot of dark matter, right, Paula? This is what we're here to discuss. But you see, dark matter and matter have a certain ratio. And the question that we have for you is, what is the ratio in the universe of dark matter to visible or ordinary matter? And the poll is now active for you to respond to. And we'll come to the answer in just a bit with our guests.
Right. Our first guest today is a theoretical physicist who has worked at CERN and is now at Sorbonne in Paris. He's Italian, Marco Cirelli. Marco, can you hear me?
Yeah, sure.
That's great. I can hear you loud and clear, Marco. So before we give you the questions from your viewers, we have a video of one of our super fans on Instagram who asks a question for you. I want to introduce the subject with you with the first question from myself. That is, why you scientists need dark matter? Why is it needed to understand the universe?
Yeah, so we do need dark matter because the universe is telling us that it contains much more with respect to what we can see, much more than the usual kind of matter that we see and of which stars and planets and gas are made of. And this is actually at very different scales. So at small scales, compared to the size of the universe, such as the scale of galaxy, and then at larger scales, at the scales of galaxy clusters, and then even at the scale of the entire universe. So the evidence for the existence of this mysterious stuff is from relatively small things to the entire universe, so the biggest thing you can think of. So basically, the universe is telling us that, I don't want to spoil your poll that you just launched, that only about less than 20% of the matter that we see in the universe is made of ordinary stuff, atoms essentially. And the rest, more than 80%, is something invisible, hidden, and that does not interact with light. And that's why we call it dark matter. So it's a kind of matter which is different from the usual one, which is hidden, invisible, and does not interact at all with light. So the evidences for this are, as I said, many at different scales. Let me give you an example. So if you start thinking about observed galaxies, like the Andromeda galaxy, our nearest neighbor here close to us, we can see, or even our own galaxy, the Milky Way, we can see that these galaxies, like Andromeda galaxy, our neighbor, is a spiral galaxy which is spinning fast as a turn plate. You have to imagine that it's like a merry-go-round that spins around its center, like a disk, say. And we can measure the velocity, the speed of rotation of many stars as we move towards the outskirts of. And what we find is that even stars that are very distant from the center of the galaxy, say Andromeda or even the Milky Way, they travel very fast. They rotate very fast around the center of the galaxy itself. And this, if you think of it, is very surprising, because if you think of another system, for instance, the solar system, we know, we measure many centuries that the outer planets, such as, I don't know, Neptune, for instance, they go slowly. No? They rotate slowly around the sun because the gravitational attraction of the sun out there at the position of Neptune or Uranus is very weak. So if the planet goes too fast, it would escape, it would spin away and spin off to infinity in the universe. So we expect that objects that turn have their peripheral bodies that spin at a lower speed than the ones at. Instead, in galaxies, what we observe is that, as I was saying, even these stars spin very fast, they go very fast around the galaxy. So that means that there is some extra gravitational force, which is given by something else than the content of the galaxy, the center of the galaxy, such as Andromeda or the Milky Way. And this extra gravitational force is provided by extra matter, and extra matter is the dark matter that we assume exists.
Marco, I have to interrupt you 1 second because there is a little problem with a delay in the sound transmission, I'm told from the regie. So while we try to improve the connection with you, I just want to see with Cinzia. Marco just said that the percentage of ordinary matter in the universe, the one that makes us, the stars, the oxygen we breathe, this microphone, this book, it's only 5%.
That's
so
right.
That's
so
ordinary matter.
It's 5% of the universe, with dark matter making up about 25, 27%. So the ratio then is 6 to 1, approximately 5 point something closer to 6 is to 1. So that's the ratio that we have. So thank you to everyone who responded to our little poll. And we're going to continue taking questions from you now.
So how viewers, how did they do?
So most of the viewers responded with 25 to 1, in fact,
Okay.
which is slightly higher than we would expect. So we have a ratio of 6 to 1, which is the right answer. 25% of our viewers have gotten that one right.
That's great.
And we will now resume taking questions, and we'll answer them over the course of the evening.
Yes, okay. I will wait for a sign from our technical director, technical desk, whether Marco is there. Yes, okay. So, Marco, you can keep going with your explanations, but we have a question for him from South Africa on Instagram. I don't know if you can play the question. We're playing a little video from one of our Instagram super fans of the CERN Instagram account who asked a question for you, Marco. Go ahead. So Massimo from South Africa asks,
Hi CERN, my name is Massimo Nunes. I'm from Cape Town, South Africa, and I've just woken up and it's cold. So once we figure out what dark matter is, how it interacts with other particles, and how we can manipulate it, what will be the application of it one day? What's the desired application? Hi CERN, my name is Massimo Nunes.
okay, so Massimo asks basically if there are already any technical applications from dark matter. Marco, what do you say?
Well, not yet. Not yet. Let's see. We can be hopeful, but let's say that for the moment, no, we have no idea. First of all, we should discover this stuff, and then when we have discovered it, let pass a few years. I'm sure that there will be some technical application. You know, this is always the case. Now, things that are discovered at CERN, or even before, things that are discovered by fundamental scientists in fundamental science, usually they're useless, and this is why they're beautiful. This is why they're interesting. But then at some point, let's go down a few decades, they become very useful. Take examples like the laser or quantum physics or even more electricity and everything else. So not for the moment, but I have good hope.
But it's certainly a legitimate question because there are even applications of relativity. For instance, I know that our navigation system, like the GPS, would not work if there were no relativistic corrections in the calculation that measures our distance and shows our way. But surely for dark matter, we are really at the frontiers of knowledge. It's for the moment an hypothesis. It's a very, very well supported by observations, but we haven't discovered it yet. And thank you very much, Marco. Keep following us on your YouTube channel and or Facebook or Instagram. It's now time to introduce another guest, this time in person. So Ajit and I are maybe wearing a mask before welcoming Joachim Kopp. Okay, so stay tuned, and Marco, thank you, and see you one of these days when you can come to CERN again. And it's now time to have our first guest in person. Who's going to stay with us for quite some time during this live because he knows a lot about the subject. We have to wear our masks.
It shouldn't be. No, it's more of a stream issue. Hello? It's like living in blocks. It's not depending on us. Hello? Attends. Tu me dis quand t'es en ligne. En ligne? Ok, ben j'envoie.
We are back, and due to some mysteries more mysterious than dark matter itself, we were cut. But we keep going, and I was about to introduce, after saying bye to Marco, our in-person guest, a very, very knowledgeable person who works on dark matter every day. I'm very glad to introduce to you Joachim Kopp, who is a theoretical physicist from CERN. Hi, Joachim.
Hi, Paula.
Hi, thank you for joining us. So you are really working with lots of mysterious things. You work with neutrinos, you work with dark matter, and you try to make sense out of it, taking all your clues from all the experiments that are searching for them. How do we, what do we search? What do these experiments are looking for? And what do you theorists tell them to look for?
Well, we don't know exactly what we are searching for. This is exactly what makes this field of research so interesting. But from the observations that we have, and to which Marco alluded already, we know that dark matter must have certain properties. The first property is that dark matter should be cold. Now, what does cold mean? As you may remember, when a substance is cold, it means that the particles that make it up are moving very slowly. For instance, cold air means that the air molecules are moving extremely slowly.
Joachim had some images. Can we show the images, please?
So, as I said, the temperature of an object is related to how fast the particles in it are moving. So the fact that dark matter is cold, this means that the dark matter particles are moving relatively slowly, at least slowly for astrophysical standards. The second property of dark matter that we can infer from the observations that we have is that it should not carry an electric charge. Because if it did, it would couple to photons, to light. And so we would be able to see it, so it wouldn't be dark. So with those two properties, theoretical physicists like myself basically have a field day trying to think about, okay, what could this particle be?
You're like detectives, basically. You have some clues, and then you think the scenario.
That's the general idea. That's the general idea, yeah. So we obviously start looking at the particles that we know of. We have some elementary particles here. I can maybe briefly hold this into the camera.
But they can zoom. They can zoom on you. But yeah. Yeah.
I'm not sure if this is in focus.
Yes. There you are.
So let's call that, which one did I pick? I picked the electron, for instance.
So this is a known particle.
Yeah, so I picked here the electron. The electron is a well-known particle. We know that it's part of what makes up atoms. But the electron, for instance, it carries an electric charge, so it doesn't fit the bill. And the same is true for all the other particles that we know of. There's one reason or another why each of them is not a suitable candidate for being the dark matter.
So we start by excluding.
Exactly, yeah. So we go through all of them and we say, okay, this one doesn't work for reason A, that one doesn't work for reason B, and so on. For most of them, the reason is simply that they carry a charge.
Yeah.
And so we have to come up with something new. And one possibility that scientists have come up with is the so-called WIMP. WIMP is a nice word, but in this case, it's an acronym. It stands for weakly interacting massive particles. So weakly interacting, this just means, well, it should not couple to electromagnetism, so it should not couple to photons. This is just a reflection of the fact that we can't see it. Yeah. Massive means it should be quite heavy. This ensures that it will be moving relatively slowly. So the weakly interacting massive particle, or WIMP, is one of the leading candidates for dark matter, but of course we don't know if it's the right one. And there are many others. So one second candidate has to do with neutrinos. So neutrinos are actually standard model particles. However, the neutrinos that we know of, they are very light. So even though they are extremely weakly interacting, they are too light to be the dark matter. They would be moving too fast in the universe. So for that reason, neutrinos as we know them are excluded as being the dark matter. However, there is the possibility that there are new types of neutrinos that we don't know of yet and which are a bit heavier than their standard model siblings. And in this case, those could be the dark matter. Now, a third possibility that I'd like to briefly mention is the possibility that dark matter is actually made of black holes. So black holes are perhaps among the most exciting objects in the universe. They are dark, as the name implies, so that explains why we can't see them, and they tend to be rather heavy. So that ensures that they would be moving relatively slowly. Now, the black holes that would make up the dark matter, these are not like the star-eating monsters that you might be familiar with if you've seen the movie Interstellar, for instance.
Everybody has seen that, yes.
At least everyone at CERN, I think, has.
Right.
But rather the primordial black holes that would make up the dark matter, they would be fairly small. They might only be the size of an atom or so. However, a black hole that has the size of an atom would still have a mass of about 100 trillion tons, so they would still be quite heavy. And this is only a small overview of the possibilities for what dark matter could be, and we're going to see some other options in the course of this evening.
Yeah, you have a few dark matter pins there. Some don't even have a name, some do, and we will look at them later on in the show. I think, Cinzia, now you might have already some questions.
We do indeed have a few questions, in fact, for you.
Let's start with a few questions for Joachim while we wait for the Skype with the next theorist who's going to join us as well. But
all right,
let's go ahead with one question.
If we detect dark matter particles, do we need to change our standard model completely?
Well, the standard model in itself will probably not change. So the building blocks of the standard model that are there, they will probably more or less remain in place. However, the standard model will definitely need to be extended. So it's not like we are going to forget everything we've learned over the past decades. This is extremely well established. The standard model is one of the best tested theories that we've ever had. So it's clear that most of it will remain intact. However, it's going to be extended, for instance, by something like an extra neutrino species or by a weakly interacting massive particle.
So we've understood from Marco why we need dark matter. From you, what kind of particles we are looking for. There are a few hints. And now we have somebody who is expert in telling the experimentalists, experimental physicists, for instance, those here at CERN, how to search for such a difficult thing, something that is invisible, but it's there. And we have the pleasure of welcoming here theoretical physicist Sushita Kulkarni. Hi, Sushita.
Hello.
Can you hear us?
Very well.
And that's great. We can see you, and I hope we can hear you loud and clear. So I read in your biography that you were working also in the CMS experiment at CERN. What was a theorist doing in an experiment at the LHC?
Okay, so yes, I like to think about myself as somebody who's trying to assemble a Rubik's Cube, okay? Think about the universe or everything we know of and trying to create in terms of a Rubik's Cube. So we all have played with it. It has different sides and every side has a color. And basically the idea is you want to complete the color structure by putting green next to green and white next to white and so on. So I have here a Rubik's Cube which has one side fixed to the standard model. As you can see, it has several standard sides. And one side is fixed to cosmic things that we know of. Okay? We know things like GN, we know things like CFD, so on. And the idea is every theory that we are going to write down shouldn't disturb the standard model that we know or the cosmic theory that we know. I see. Okay. So I'm going to try. Okay. So essentially, you have these two sides which are fixed, and we can write down different theories on every other side of the Rubik's Cube. Okay. And each theory comes with its own signatures. So for example, you can have a dark matter candidate that produces something called missing energy at the LHC, which is here. And if you have something like a Z prime, which is a heavy Z particle, then it can produce a dijet event, okay, so called resonance. You can have supersymmetry, which is also very well known. It can also create missing energy. Sometimes it comes with a long-lived particle or charged particle, and you can look at it in long-lived sources and so on and so forth. Okay. So now the idea is if you find signatures at the LHC, you will be able to complete a phase of the whole Rubik's Cube. And we don't know how big this Rubik's Cube is, how many faces it has, or how many dimensions it has. Or maybe there is a theory that we have not even thought about yet. And the experimentalists are going to basically tell us that we have found a green color, and all our theorists are going to construct theories that will give you green signatures. Okay? So
I
that,
like the Rubik Cube approach. It's very, very nice.
thank you.
I
So
know you
I hope
prepared another trick for us.
Suchita,
Yes.
before you show us our next trick, we launched a small poll once again for our audience who's watching, and I thought you could also tell us a bit about this. So we asked our viewers, which of these is not a way to look for dark matter? And the options they were given were break it, make it, bake it, and shake it. And happily, 50% have chosen bake it as the wrong answer. And of course, they're right. It is indeed the wrong answer. So could you tell us a bit before you go into the next one about these three different ways for us to look for dark matter? How do we break it? How do we make it? How do we shake it?
Right. Okay. Yes, indeed. So the nice thing about dark matter, right, as I was telling you, different colors of different theories, is that dark matter gives us different signatures to look at. Okay, I gave you one signature here where we have a neutralino. It can create missing energy at the LHC, but it can also create signatures at what is called as a direct detection signature or direct detection searches. So what you want to do is you take the dark matter and you want to discover it in different ways. Okay, so we all sort of know a little bit about LHC. At the LHC, we have two protons which are going to collide with each other, and they can create dark matter particles. Okay, and this is the way we call it make it, because we start with something where dark matter doesn't exist, and then we end up with dark matter particles in the detector. You can start with dark matter particles, and just like you created dark matter from protons, you can create standard models from dark matter particles. So you have broken dark matter particles down to standard model particles. Okay. And finally, you can take a dark matter particle and scatter it on a standard model particle, just like a billboard, right? And that would be a way of shaking dark matter particle, which is to say you don't actually break it or you don't actually make it. You essentially just go from one state to the other. So that's the shaking.
Back to you, Paula.
I'm sure that you will find one day a way to bake dark matter. Suchita, I have to say bye to you because we are a bit late. We lost some minutes due to network connections. And I know we have our super surprise guest waiting for us to contact us from Houston. So we can go to the next part of our show. So we've seen why we need dark matter, what do we search, and Suchita told us how do we search. And now we are going to see a couple of experiments, both very, very directly related to CERN, that are looking for dark matter in space and in the sun. And I'd like to see a clip that will introduce us to the next subject very, very nicely.
On the 20th of July
Dark matter in
2019,
space
exactly
and in the
50
sun.
years after Neil Armstrong became the first man to set foot on the moon, Italian ESA astronaut Luca Parmitano took off from Baikonur in a Soyuz for his second long-duration stay on board the International Space Station. During his stay on the International Space Station, Luca Parmitano also performed 4 spacewalks to repair AMS, the Alpha Magnetic Spectrometer instrument mounted outside ISS. This subatomic particle detector looks for dark matter, antimatter, and cosmic rays. The AMS spacewalks were some of the most complicated EVAs ever, as the instrument is difficult to reach and was never designed to be maintained in orbit. A daunting task and a true engineering challenge, particularly considering the critical situation Luca experienced during his previous mission, when his helmet filled up with water during a spacewalk. However, this time, all EVAs went according to plan.
Congratulations to all those that worked to achieve the EVAs and the point that we are at. And hopefully with the next EVA, we'll find out that all this work was put to good use. Thank you so much to everybody.
Thanks, Luca. Great words. The team very much appreciates that.
On the 20th of July 2019, exactly 50 years after Neil Armstrong became...
And that was the alpha magnetic spectrometer experiment. We are waiting for a connection with astronaut Luca Parmitano, who had a major role in replacing a vital component of the AMS in space with a series of exceptional spacewalks that were deemed even more difficult than the one to replace the Hubble Space Telescope mirror. So to talk about the alpha magnetic spectrometer, while we wait for Luca, we have an alpha magnetic spectrometer scientist. I can see her, Mercedes Paniccia. Of course, you are not in space. You are not far from here in Geneva, because you are one of the collaborators of the AMS experiment from Geneva University. Mercedes, tell us more about AMS and how do you search for dark matter in space?
Yes, good afternoon. So AMS is like one of the particle experiments, detectors that are at CERN, but we just made it smaller and put it on the space station. So we measure all these cosmic rays that are particles, and 90% of them are protons, and then we have small amounts of nuclei. And the rarest particles are those that are produced by collision of these cosmic rays with the interstellar matters, like positrons, antiprotons. And this is actually in these rare cosmic rays that we look for the signal of annihilation of dark matter particles into ordinary particles. So they will produce pairs of protons and antiprotons, or electrons and positrons. But we will not be able to look to find for the tiny signal of dark matters in the protons or in the electrons. That's why we need a magnetic spectrometer that is able to measure also the sign of the charge of the particles, and so to measure precisely positrons, the amount of positrons, the amount of antiprotons, and to look for anomalies in the amount of the flux of these particles that we detect in space.
Particles that are candidate dark matter particles. And I know because I had the very big luck of being there when the space shuttle was launched in May 2011 with alpha magnetic spectrometer on board before it was installed on the space station. I was there with your boss, Professor Sam Ting, a Nobel laureate for physics, and I gave him, as a sign of luck, a particle plush called Neutralino. We here have a pin of a Neutralino. And is this the particle you're looking for? Is this still your Graal?
Yeah, yes, exactly. We are looking at what we call WIMPs, these weakly interactive massive particles that would collide between themselves and can annihilate or even decay and produce ordinary particles.
That's great. That's amazing. Mercedes, I just said the AMS was launched in 2011. A few months ago, Luca Parmitano has done 4 spacewalks to even make it better, more performant, so that it can stay in space for longer. But since 2011, you must have collected a huge amount of data. What did you make out of this data? Did you reach any conclusions?
Yeah, so far we collected more than 160 billion of cosmic rays. This is a huge statistics. So we have confirmed the excess of positrons in cosmic rays, and we are investigating the nature of these positrons, looking at other species in cosmic ray, mainly nuclei that are, as positrons are produced by the collision of cosmic rays with interstellar medium. And this can tell us what happened to cosmic rays when they collide with interstellar medium, when they propagate. And so to understand how much of the excess that we observed on positrons can be due to a dark matter signal. And also we did a precise measurement of the antiproton spectrum. And up to now, there are some theories that have studied this signal, and they may think that there could be some hint of dark matter at low energy in the antiprotons as well. So
thanks a lot,
everyone is
Mercedes. I know there are many publications from the IMS collaboration about this excess of positrons that hints at the presence of dark matter. You need more data, I know, to keep going with the search. In the meantime, I have to leave you because we have somebody from Houston waiting to call from us. And I'm very, very pleased to announce that we are ready to talk to, as astronaut, Luca Parmitano, who, as we said, had a great role in the alpha magnetic spectrometer because he's the one who made it more performant by replacing its cooling system, a very important object. Hey, I see Luca. Hi, Luca. Can you hear us?
I can hear you. There is a little bit of a delay, I think.
That's great. I'm really super intensely happy to have you celebrate Dark Matter Day with us at CERN. And I took the liberty of including you in our array of dark matter hunters, because even if you're not technically a scientist who studies dark matter, you made a major contribution to one of the most fantastic objects that are looking for dark matter and doing it in space. You did an amazing task of replacing the cooling system of this alpha magnetic spectrometer by acrobatic spacewalks, unprecedented and extremely complex. So what does the term dark matter inspire you of?
Well, I was muted.
We can hear you now.
Okay. Well, as you can see, I'm actually wearing the polo shirt that I had on orbit during Expedition 61 when we performed the EVAs. Yeah, I thought that it would be my way of celebrating Dark Matter Day. I was thinking about it the other day because I actually rejoined with my crew and with Drew Morgan, Dr. Drew Morgan, who was my crewmate during the EVAs, and we were thinking back about when we were in Aachen, talking to Professor Samuel Ting about AMS. He gave us a very quick lesson, about 30 minutes or 45 minutes of lessons about what AMS had already done in terms of destroying some of the theories that we had about the universe and letting us come up with new ones. And that sense of wonder of how much an experiment can contribute to understanding the universe, that stayed with us. And since the very beginning, Drew and I felt a lot of responsibility into making sure that we would take the greatest care into trying to fix and upgrade AMS-02.
And we are very, very proud of you because you've been really closely part of that adventure. We've received an enormous amount of questions from you, from our Instagrammers. Some of them, we call them super fan because they do follow CERN Instagram really regularly and they participate, they engage a lot. And so now we ask them to send a video with their questions. So we're going to play those videos with questions for you. I hope it works. If it doesn't, we have the text and we can read the questions.
Hi, I'm Loredana and I'm from Italy, like you. I wanted to ask you, how does the upgraded thermal tracker pump work? I love your job and I love physics. Bye. Hi, I'm Loredana and I'm from Italy, like you.
Did you get that from Loredana?
The video?
Yeah, did you see it?
I did not see the video.
Ah, okay. So she was asking, how does the upgraded thermal tracker pump work?
Okay, I'm trying to look for the questions, but I couldn't find them. So what was the question again?
It was, Loredana was asking, how did this upgraded tracker pump work? What's the function of it in the whole AMS?
Oh, okay. So the upgrade works like this.
This cooling system, you must have studied it a lot, right?
I did. More than I ever thought about studying any air conditioning in my life. So
right.
I know it better than the air conditioning in my car, for sure. So in order to capture these very, very elusive particles, AMS needs to be really, really cool, really cold. And so it was sent up with 4 pumps that would continuously send in a loop carbon dioxide, liquid carbon dioxide, so that the cold carbon dioxide from the radiator would just collect all the heat and then irradiate it back to space, so that to keep the AMS really cool. However, AMS was built to work for 5 years, and the pump were made to work for 5 years. And that's what they did. They worked for 5 years, they gave us all this information, and then they slowly started degrading. So what we did, we can compare it to an open heart surgery. And our heart is a pump. So we went to AMX, we opened it up, so we cut through the skin, we opened it up, we cut all the tubes that connected the original pumps to the cooling system, and then we came in with a new pump that is actually made up of 24 pumps.
Wow.
Each one capable of sustaining the cooling, and then we connected the new pump with new tubes to the old tubes. So we installed the new heart, and then we restarted it.
And all this was done in space, in microgravity, with a lot of equipment on you, with your EVA suit. And also, it took more than 1 spacewalk, right?
Well, we didn't know at the beginning how long it was going to take, because we thought that a lot of things would go wrong. So we planned to do things in blocks of activities. The first day, we went out for 1 EVA that we called the opening salvo. And that's when we went out with all these special tools. And not only we were using our spacesuit, in our gloves, in our pressurized suits, we also had to make sure that we didn't lose any of the bolts and nuts and washers that closed the AMS, because it was never meant to be upgraded. So we took out a lot of bolts and a lot of nuts and a lot of washers. We captured them without losing them in space around us. And then we opened it up. And then we knew that we could access the tubes that we were going to cut. The second EVA, so that's already 6 hours of work. The second EVA, a week later, was the nail biter. That was the most dangerous in terms of creating problems, because we had to cut some tubes, but not all of them. And we had to cut them in specific places. And if we made any mistakes, we were gonna finish right there, because there was no way to recover. So we actually went in with bolt cutters, and we cut the tubes, and then we prepped the EVA for the next one. On the third EVA, so that's number 3 already, that was the money maker. That's when we went in with the new pump, with the new heart, and we installed it. And then the fourth one, about a month later, was called the closing act, because literally we were going to close everything down with a special cover to keep it cool. And that was also the most surprising of all the EVAs.
Yeah, it was exciting to follow it from the AMS Payload and Operation Control Center here at CERN. It was just incredible. Also, when you jettisoned the old pump, it looked as if it was coming in our faces, because we had a huge screen. We now have 2 more video questions from Instagrammers. Let's gonna play them one after the other, and I'm gonna read the questions to you if you don't hear.
My name is Ian Sala, I'm from Spain, and I'd like to ask Luca Parmitano, how do astronauts keep their emotional stability up, and if he's ever encountered any problem with negative thoughts or anxiety while in space?
Okay, this is Guillem from Spain, visibly, who asks, how do astronauts who do complex things like you in space, really outside the station, keep their emotional stability, and how do they handle Any moments of anxiety?
That's a great question from Guilhem, and I would say that the job is done before going up in space and even before becoming an astronaut. The job is done by the people who select the astronauts. And the reason why I'm saying that is that you can test the astronaut candidates and people who apply for their emotional stability in general. And you want somebody that is actually quite normal. You want a person that is stable, but not robotic. Because you have to work with people, with all kinds of people. So you want somebody that can be relaxed when it's time to be relaxed, but can be professional when it's time to be professional. And that is also capable of feeling a certain detachment when it comes to performing a task, so that you can do it without worrying if you're going to make a mistake before you make the mistake, because that's the easiest way to make a mistake, is when you worry too much. You have to go in trusting your capabilities and the training that you have received. Like a doctor or a surgeon or an engineer, you know, if you're going to build a skyscraper, you can be anxious about whether your calculations are good. You have to trust that your training did it right, and your team and everybody else who supports you.
Thank you for this great answer, Luca. You're certainly well placed for that, because you were a test pilot before becoming an astronaut. So I guess you had all the qualities, and you showed that very clearly with 2 amazing spacewalks, 4 for AMS and the previous one with the water in your helmet. That was really incredible. Unprecedented cases both. So really, we are very proud of you. There's one last question from an Instagrammer, and then we'll leave you to your job there in Houston. Let's play that.
Hello, my name is Diego. I am from Mexico, and my question is, do you play any musical instrument?
Amena, a leisurely question from Diego, who asks whether you play any musical instrument.
Okay, so I have to be very honest. When you ask me if I play, I'm going to assume that I can at least come out with some sound out of it. and in that sense, yes, I entertain myself with the guitar and the keyboard or piano. I used to play the bass guitar in a band when I was young, and then I even had hair. And then recently, I even had fun playing the harmonica. Now, I wouldn't consider myself as a musician. Not even talking about a talented one. I'm just saying, having any capability. I just do it for the love of music. Definitely not for the love of people around me, because I would say that most people just tend to stay away from me when I play any instrument.
Exceptional
the guitar,
in everything.
The piano,
Come on,
the bass
Luca.
guitar.
But I'm sure you love music,
Exactly.
because I remember you had a playlist on the space station that was really good, really, really good music. So you appreciate music. Okay.
I even rapped together with Giovanotti from the space station, and then I even held a DJ set.
Fantastic.
But again, that's my way of getting out of my comfort zone.
Thank you, Luca. Thanks for getting in touch with us from Houston. Thanks for celebrating Dark Matter Day with the Mission Beyond T-shirt, sweatshirt, whatever it is. And hope to see you soon at CERN once again. You already came here, but next time you come, we have to take you underground to visit the LHC. It's promised.
Absolutely. Thank you for having me, and good luck with the rest of the Dark Matter Day.
And good luck for your future missions. Bye. So thanks to all the people who asked us questions for Luca. They were absolutely marvelous. I have a question for Joachim while we wait for our next connection.
Sure.
What if he could play well music, and if he played during a spacewalk? Would we hear anything?
No. So space is almost empty, so it doesn't carry any sound. Sound is essentially oscillations of the air around us. So if he played the guitar in space, we would not be able to hear him, unfortunately.
That's a great explanation.
So we should ask him to play instead when he visits CERN, then he can play in the LHC tunnel.
All right, we'll see. we'll see. So we've been talking about looking for dark matter particles in space. We have a candidate here, the Neutralino. There is another pin here which says Axion. It's another dark matter candidate. Where do we find Axion, Joachim? If they exist, where are we looking for them?
Well, like for all dark matter particles, we are looking for them in many, many different places. One of the places we are looking for them is in space. For instance, there would be axions, or could be axions being made in the sun, if they exist. So one of the exciting possibilities to search for axions is to see if there is anything unusual coming out of the sun. It's very difficult to detect, of course, because it's still dark matter, so it's still extremely weakly interacting. So we need really ingenious instruments to search for this kind of dark matter, like for all kinds of dark matter. And
that we've seen dark matter in space with the alpha magnetic spectrometer. We have at CERN an experiment which uses an LHC unused dipole to look for these axions. It's called CAST. We are waiting for the connection with them. And we also have a little clip about CAST. Let's show the clip, and then we talk to the physicist who is waiting for us not far from here, around the LHC on the surface at point 8. So, yes. As I said, they are using a dipole from the LHC. So you must have recognized the blue tube. It's an LHC dipole. In the LHC, there are 1,232 of those, and their job is to keep the beam in the trajectory, right, Joachim? But the people at CAST have taken one of those, and they're using it very differently. They're using it as a telescope. Can you explain a bit this procedure?
Right. So one of the special things about axions is we cannot see them, but we can turn them into something that we can see. So if axions exist and they travel through a strong magnetic field, an axion can turn into a photon, one of the particles of light. And that way, we would be able to see it. So the special thing about the LHC magnets is these are extremely strong superconducting magnets. So they produce a very, very strong magnetic field. So the idea is we take one of those magnets, we make sure it's properly sealed on all ends so that no other particle can get in particular to make sure that none of the ambient photons can get in, like the photons from the light bulbs in the experimental hall, for instance.
Right.
So, however, axions, they are dark matter. They are extremely weakly interacting, so they would still be able to get in. They would enter the magnetic field, they might be converted into photons, and then at the very end of that LHC dipole, we place a photon detector. If there are no axions, then that detector should just stay dark. It should not detect anything. However, if axions exist, we might occasionally see a small blip of light coming from an axion converting into a photon. And the reason you've seen the telescope moving around all the time, that's just because it has to follow the sun, right? We're looking for axions that are produced at the very core of the sun, and so we have to point it to wherever in the sky the sun is.
Ah, it's amazing. So it really qualifies as a telescope.
It definitely does. A slightly unusual one, but it is a telescope.
And I can see in the screen that we are connected to the CAST experimental hall, and I see one of the CAST physicists, Sergio Arguendis. Hi, Sergio, and thanks for being with us. Can you hear me?
Yes, I can barely hear you, but I can. Can you hear me?
Yes, we can hear you very well, and we have seen a little time lapse of CAST being moved around following the sun, and now we see it just behind you. Tell us more about this incredible telescope.
Okay, yes. So as it was mentioned before, we're right now at point 8 at the French side of CERN. We are at the CERN Axion Solar Telescope that you can see on the background. Now, in this experiment, we look for the axion dark matter particle, which was first introduced to solve the strong CP problem of the standard model. And later on, it was seen that it was also a suitable dark matter candidate. So the name axion actually comes from this washing brand, because the person who proposed the axion said that we are washing two problems of the standard model, and that's why they gave the name to this particle. Now, how do we look for the axion here at CAST? And it was mentioned before, the axion can transform into a photon in the presence of a very strong magnetic field. Now, where can we find the magnetic field? And one of the answers is our sun. Inside of the sun, there are some processes where the X-rays are produced, which are photons. They interact with the field of the sun and transform into axions. These axions interact with the particles of the sun. They escape. So you can imagine the same kind of source axions. What do we do here? In the diagram you can see on the background, on the clip, sun comes. We move the magnet left, right, up, down, and we try to follow. However, it's very heavy, so we angle. So we was able to on. Now, what happens following the sun? Here, you have the axion into the magnet. Then they.
Your mouth.
Now is better?
Yes, that's perfect. We hear better. You must use it as a singer.
Okay, so the axions, they enter the blue magnet that you see on the background. They can transform back from axions into X-rays because they feel this is a strong magnetic field. And what we do is we put some X-ray detectors at the end of the magnet. So if you can see over there, at the end of the dipole magnet, we have some X-ray detectors where we measure the energy, and we in simple words compare the measurement between the magnet on and the magnet off and see if there's any difference between them. That's in simple words for axions. But here at CAST, we also look for relic axions, which are axions produced after the Big Bang, not just the solar axion. The second method, again, are axions coming into the magnetic field. They transform into photons, and if they have the right wavelength, they will rest inside of this cavity. We have an example, and then resonate with an extra power that we can measure. And like that, we can also search for relic axions and not solar axions. So that's more or less what we do here at CAST.
For this super rapid guided tour of your experiment. I think we have a question for you from our viewers, Cynthia.
Yes, Sergio, thank you very much for taking us through. The question that we have is, how long has CAST been running? And cheekily, how close are you to finding axions?
Sorry, can you repeat it?
Yes, the first question is how long has CAST been running? And the second question is slightly cheekier, which is how close are you to finding axions?
Okay, I didn't understand the first question, so I hope you can repeat it later. The second question, if I'm correct, is how close we are to find the axion.
That's
yes,
right, yes.
Correct.
Okay, so right now we have what we call the axion space search, because we don't know what is the mass of the axion and we don't know what is the coupling, meaning the probability of changing axions into photons. Right now, the theory predicts a region where you are highly probable to find the axion. Right now, CAST is still a bit far away from this region, so I would not say that we are that close, but we're improving our detector. There are other new facilities that are going to be built in the future, like IAXO, which give us a better chance of seeing the axion at the moment. So we keep searching for the axions, and we are trying to improve our sensitivity to reach this theoretical line where we're supposed to find the axion. And the first question was?
How long has CAST been running?
You got it? How long has CAST been running?
Wait, can you repeat it?
How long has CAST been running?
So actually, that's a very good question, because this year, if it was our 20th anniversary, so we have been running already for 20 years.
So already 20 years ago, you had a dipole from the LHC?
Wait, I cannot hear you
You
right
had your
now.
telescope already 20 years ago?
Sorry?
With the same instrument? With the same instrument?
No, like the magnet is the same magnet. However, we have improved our detectors. So we changed the X-ray detectors for different types of detectors so we can have a better resolution. And in the recent years, we also included this other type of method to search for other axion masses with another type of method. So it's the same magnet, but we improve our detection and the way we detect. So that, like that, we can improve our sensitivity.
Thanks a lot, Sergio. This was fantastic. I wish you a lot of luck as to all dark matter hunters. The hunt is hard, but I'm sure you will succeed one day. Thank you very much. Okay, so let's resume our marathon with dark matter hunters. We've seen these two experiments. We're using the cosmos basically as an accelerator, generating particles, be it the sun or cosmic rays from anywhere they come from. Now, let's get to what is even closer to CERN core business, particle accelerators, and looking for dark matters with particle beams. And we are going to start with experiments that are using, in the CERN accelerator complex, if you send the animation, they're using this super proton synchrotron. Sorry, not the SPS, yes, the super proton synchrotron beam we see here. So they use the beam of protons from the SPS. And the experiment we are now talking about is called NA64. Can we take a break and take a look at the movie of NA64 while we get ready to talk about how to find dark matter with particle beams?
The existence of dark matter is one of the biggest scientific mysteries today. We know that 85% of the matter in our universe is made of a form of invisible matter because we observe its gravitational effects. Many theoretical models try to explain it, but to date we do not know anything about its composition and its origin. NA64, a new experiment at CERN, is now investigating an intriguing theory.
The very exciting and intriguing possibility that in addition to gravity, there might be a new force between our visible matter and dark matter, which is transmitted by a new photon-like particles, which we call dark photon or heavy photon or paraphotons. There are many different names for these particles. This experiment, it's apparatus which is about 30 meters long, and the main idea is that we search for so-called invisible decay of dark photons. And these particles could be quite light, below 1 GeV. And what is most important, that these particles could be searched for at low energy experiment, with fixed target experiment.
Na64 uses a beam of proton from CERN's SPS, the super proton synchrotron, which are made to collide with a fixed target. These collisions produce electrons that are selected by a 400-meter-long beamline, taking these particles to the experiment.
Our group is responsible for tracking the incoming particles to reconstruct the momentum of the particles before it is dumped in the ecal.
So what you see here is the beam pipe where the beam is coming. The electrons are deflected by two magnets, which are about 15 meters upstream. The purpose of that is really we need to be sure that what we get here are electrons of 100 GeV. So in this magnet, when the electrons are deflected, you generate synchrotron radiation, and this we detect with this detector here.
We count every electron, and we look at the energy deposition in our apparatus for each electron. So the idea is that when the high energy electron collide with the active target, which is electromagnetic calorimeter, it's create in this high energy collision with the nuclei, create dark photons, which carry away from the setup significant fraction of the primary energy. So the experimental signature of the existence of A prime is an event with such missing energy, and we search for these events with this setup.
The large missing energy looked for by Na64 cannot be attributed to an ordinary process, and would therefore be a strong hint for the dark photon signature, which, if confirmed, would provide an interesting solution to the mystery of dark matter.
And I'm very pleased to welcome here one of the members of the Na64 experiment, Dipanvita Banerjee from India, but actually you did your PhD thesis from ETH Zurich at that experiment. We saw you very young. You're still young, but you were you looked very young at in that clip.
Sure.
So I know you brought a few slides that we can call up because you have to tell us how does Na64 works.
Sure. So, as we know that the standard model of our particles has many particles and interactions in it. So it's not very unnatural to think that the dark matter can also exist in the dark sector with its own particles and interactions. And so just like in our standard model, we have the photon, which is the mediator of the electromagnetic force. In the dark sector, we can have a dark photon, which mediates the force in the dark sector of particles. If there is a mixing between our normal photon and the dark photon, this can be searched for in any interaction that produces photon in the experiments. So Na64 is one such experiment which actually looks for a dark photon in the interaction of particles with normal matter. So if we can pull up the slide, we see that in the first, Na64 uses a 100 GeV electron beam, which comes from the H4 beam line at the CERN SPS. And this goes through the magnet and is dumped against the target, which is the ecal. When it passes through the magnet, it deflects according to the momentum, so we can reconstruct the incoming momentum of the particle. While it is passing through the magnet, it also emits synchrotron radiation, which depends on the mass of the particle. So this also helps to ID the particle species, because as we know that the beam is not 100% pure, so we can also have contamination of pions in the beam. So the synchrotron radiation helps to suppress this hadron contamination.
Okay.
Once the electron is then dumped in the ecal, there's interaction which produces photons, and via mixing, it can produce a dark photon, which subsequently decays into dark matter particles, which goes to the rest of the detector undetected. So the signal would be that we have 50% of energy in the ecal and missing energy of more than 50% in the rest of the detector. So like this, we can search for the invisible channel of the dark photon when it is decaying to dark matter particles. There's another way to search for dark photons is by looking at the visible channel. So the beginning part stays the same. The electron comes in, we track it through the magnet, it is dumped in the ecal, there is interaction where the dark photon can be produced. Now in this case, the dark photon passes through or escapes the ecal one and passes through the veto, where it leaves no signal because dark matter won't interact with our normal matter. And then it can decay into E plus E minus pairs, which is then again tracked in the trackers downstream, and it deposits the energy in the ecal 2. So if the energy of ecal 1 plus the energy of ecal 2 gives us back the energy of the particle or the incoming beam, and we have no signal in the veto, then it's almost like a light shining through a wall. And this would be the signal for a visible channel for dark photons. For the future as well, NA64 now has extended its search with a muon beam, or they plan to do it for 2021 and beyond, where they are actually looking for a dark boson, the Z mu, which couples predominantly to the second and third generation of leptons. So this is the muons and taus. That's why using a muon beam is a natural choice. So one can use a 160 GeV muon beam. The beginning part, again, is the same to track the incoming muons. Then once it interacts in the ecal, the muon no longer is stopped at the ecal because it's a heavy particle, it goes through matter. So we have to track the momentum of the scattered muon. And in this case, if the scattered muon momentum is less than 50% and the Z mu, or the dark matter candidate, carries rest of the momentum, we have missing momentum, which would again be a signal for dark photons. So these are the main three ways that NA64 plans to look for dark matter.
This is surely a super smart trick to hunt for something invisible. I'm intrigued by the word dark photon because I usually associate photon with the concept of light, but this is clearly something that doesn't carry light, right?
No. So photon is also a force mediator in our standard model. So it is basically an interaction, or it carries the interaction between normal matter. So dark photon is a similar force mediator in the dark sector of particles, which mediates interaction between dark matter particles.
And is also massless, like the photon.
Well, we are looking for sub-GeV masses, so we don't know.
Right.
There is a whole range of masses the dark photon can exist in. So we are looking for sub-GeV masses or around 100 MeV or so.
Yeah, it's a very, very smart trick. Achintia, do you have questions from the audience for Deepanvita?
Yes, we do. We have a few questions. I'm going to throw a few of them at you. So one question is dark matter, this is a question from Francisco, is dark matter surrounding me and everything around me?
Well,
is it here, around us?
Well, dark matter interacts with normal matter via gravity. So if it was present in a huge amount, let's say around us, then we would feel the gravitational interaction with us. But we, of course, see it in our galaxies, and we can look where the cluster of dark matter is by looking at the gravitational interaction of dark matter with normal matter. So, yeah.
I even know there is a map.
Yes.
There is a very well-defined map of where it is in the universe.
Yeah. If you look at the velocities of the stars in our galaxy, in principle, we expect, I think you will also show it in the future. Yeah. Sorry. Okay. I think you will also show it that the spiral velocities of the stars in the galaxy should, in principle, fall. But if you look at the velocities as we go outside our galaxies of the stars, then it stays more or less constant. And this points to the fact that there are some dark matter or invisible matter, because there is no luminosity coming from these masses, that is present in the outer galaxies as well, which keeps this spiral velocities kind of constant.
And we have another question, which is from someone who hasn't given us their name. Is there any possibility of interaction of dark matter, or can an interaction exist that we are not aware of?
Surely an interaction can exist that we are not aware of, but for example, NA64-like experiments are looking for dark matter interactions with normal matter that is beyond just gravity. So there are models which postulate that there can be dark sector of particles, so a whole particle zoo of dark matter in principle, and they can have self-interactions as well. So dark matter particles can interact with each other.
Themselves, okay.
And also with normal matter by new forces, which NA64 is looking for one such example of that.
And this was another question as well that we had, which is could dark matter be associated with a fifth force? Because so far we know of 4 fundamental forces in the universe. Could dark matter be associated with a fifth force as well? And
yeah,
that's
exactly.
You think it could be?
Yeah.
Great.
Thank you for sending all these questions. So we've discussed the dark photon. Deep and Vita, stay with us while we look at another experiment here at CERN, more recent than NA64, that is also looking for dark photon. It's called Phaser. We have a clip to show a little bit how it works. And then we have one of the collaboration members, a physicist from Phaser, that is joining us just after the clip.
So this is an assembly test of the new Phaser experiment at CERN, which is an experiment that's designed to search for new light weakly interacting particles that wouldn't have been able to be discovered by the other experiments that already exist at the LHC. Phaser has been designed and constructed over the last 2 years. This is the final assembly test that we do before we start to install it into the LHC tunnel, which should be completed by the end of this year. The aim is for it to take data during proton-proton collisions in the LHC for the next 3 or 4 years, and within this time it should be able to either discover new particles or to set constraints on the models that predict new particles, particularly related to dark matter. The kinds of particles that this experiment would be able to see, if they exist, are related to dark matter, which is one of the big questions in physics at the moment. And so the best type of result that we could have is to observe a new particle that would help us to explain dark matter in the universe that we observe.
And we are joined here in the studio by another dark matter hunter. I'm very pleased to introduce to you Michaela Quetsch-Meiteland from the Phaser collaboration. Hi, Michaela. Thanks for joining us on Dark Matter Day. We've just seen your colleague Jamie Boyd illustrating the experiment. First of all, what does Phaser mean?
That's a very good question. So Phaser is the newest LHC experiment, and it stands for Forward Search Experiment. So it's looking for new particles, weakly interacting new particles that are produced in the very forward region of LHC collisions.
So you take beam from the Large Hadron Collider, while we've seen Deep and Vita takes beam from the previous ring, the Super Proton Synchrotron. But we saw your experiment is not yet in position to take beam, right? That was a surface area.
No, that's correct. So this is a completely new experiment. It was approved by CERN only in 2019, so it's actually been constructed very, very quickly for LHC experiments. And relative to the scale of huge LHC experiments like ATLAS and CMS, it's very small. It almost fits on a tabletop. And we're currently, so we finished the photos that you've seen are the first assembly of the detector. And around about next week, we'll start installing it in the LHC tunnel. So it's actually located in an unused tunnel that's just next to where the LHC beam goes around. So this used to be used in the days back when we had the LEP collider,
right?
Where electrons used to be injected into the LEP ring.
Right.
And this is now just an abandoned tunnel doing nothing. And it's a really unique place to look for new physics because we essentially take proton-proton collisions from within ATLAS, so point 1 of the LHC. And then I think we might have a slide that shows an overview of where this is in the LHC
Our viewers
ring.
are seeing your slides.
So I think in the next one where the green is.
Yeah.
But so essentially we have particles produced inside collisions within ATLAS, and then a new particle would fly down the beam pipe and then be detected within Phaser, which is the image that you see right now. So this is what the Phaser detector will look like when it's fully installed. And you see it's in a little trench, and this is to be in the line of sight, what we call of the collision. So if a proton just kept going after going through ATLAS, this is what it would look like.
You have a dedicated beam line for you that goes through Phaser?
It's not a beam line, no. So what we're looking for is weakly interacting new particles. So actually, they would be produced within collisions in ATLAS, but then just go flying down the beam pipe through concrete because it won't interact with anything. And then we look for it decaying potentially in our detector.
A super smart way as well of looking for the dark photon. I'm sure Cinzia has a few questions from our viewers for you.
Yeah. So thanks very much for joining us. And one of the questions that we have is, how would we be able to get a greater idea of dark matter with current technology? And I think that's quite interesting with regards to Phaser because you're trying a different approach to some of the other experiments here. So where are we with current technology in the search for dark matter in the context of CERN? and how can we use all of these different techniques in looking for dark matter?
I think that's a really great question and links very well to phaser, because the whole idea behind the Forward Search experiment is to really exploit these collisions that we have going on already and try to look at the problem in a new way. And so I think there's really a wealth of experiments, at CERN that are starting to look at kind of unique ways of targeting the problem of dark matter. Phaser is just one of the newest ones, but there are many, in the works over the next 5 to 10 years that will also use kind of new ideas like this in order to try and really pin down the search.
And there's another related question that's just come in for you, in fact, which is, how will the phaser experiment expand the scientific potential of CERN's accelerator complex?
Well, that's also a very good question. So phaser, because of where it's located and the distance it is, so it's actually 480 meters from the Atlas collision point. So this means that it's sensitive to very long-lived weakly interacting particles. So something really has to be produced and travel 450 meters through 100 meters of concrete and rock and then decay within our detector. So it's really probing a very unique region that's never been probed before. So we're really excited for first data because, who knows what might be there.
And why that particular distance?
Well, so this is because we had already this disused tunnel from the LEP era, which turned out was a very ideal location to put a detector, partly because this is where we have very low backgrounds from the LHC beam as well. So we're essentially a zero background almost experiment compared to other LHC experiments. And so this is a very quiet environment. So if we see a signal, it's probably some new physics.
Right, and there's another question here that I will raise if I can find it, but it comes to both of you, which is, what are the different sort of candidates that we have for dark matter? Because all of these different technologies are relying upon different candidates decaying in a certain way, producing certain signatures, right? So you don't have to go through the entire breadth of dark matter candidates. What are some of the interesting candidates that we're looking for here at CERN?
So as she said, that they're looking for long-lived dark matter particles when it has to go through a large distance and after that it decays in the detector. For NA64, for example, it's looking for shorter-lived because the detector itself, once the beam hits the target and then it decays, the distance is few meters or so. So dark matter candidates can exist over 75 orders of magnitude of masses.
Wow.
So almost.
It's enormous.
Yeah, so that's why we need these complementary searches to look for different mass ranges. So an N64 setup cannot look for a long-lived dark photon because the setup is just not large enough. And phaser will not be able to look for something that decays quite close to the production point. So I think that is why these complementary searches are quite important for the kind of searches that we are looking at.
Right, and of course, and CAST, as we saw earlier, is looking for something that's coming from slightly farther away as well. So different lifespans of particles. So
and also with AMS from cosmic rays. Yes, so dark matter, wherever you are, will spot you. And whatever you are, especially, that is the question. What are you, dark matter? The technical table of my colleagues tells me we have a connection working now with very far away and very deep underground with the CMS detector at the other side of CERN, 13 kilometers from where we are standing right now, and 100 meters underground. And we are here with Adish Vartak. Hi, Adish, one of the physicists from the CMS collaboration. Hello. Can you hear me, Adish?
Yes, can you hear me?
Yes, we can hear you. Not very loud here, but
is this better now?
Yes, it's not. Doesn't depend on you. It depends on our volume here. It's great to see you underground celebrating Dark Matter Day with us. Can you describe where you are?
Right. So hi, I'm Adish. I'm here about 100 meters or so below the surface of the Earth, in the experimental cavern of the CMS detector, which you can see right behind me. Now CMS stands for compact muon solenoid. In spite of the word compact in its name, it really is a huge experimental device. As you can see, it's cylindrical in shape with a diameter or height of about 15 meters. So it's really the size of a multi-story building, and it weighs a staggering 14,000 tons. Okay, so when the LHC is in operation, we have extremely energetic beams of particles, protons or heavy ions, that smash into each other head-on at the very center of CMS. These energetic collisions produce a whole host of particles. Many of these particles are already very well known to us. Some of these particles have only recently been discovered, for instance, the Higgs boson. And it is conceivable that there may be new, yet undiscovered particles that are also produced in these collisions, for instance, dark matter. Now, the role of the CMS detector is to record, detect, and measure various kinds of particles emerging from the debris of these collisions. And this is achieved through a set of concentric cylindrical subdetectors that together make up CMS. So as you can see here, the outermost and the largest subdetector is the muon spectrometer, all here in red. So this in fact lends its name to the M of CMS. And as the name suggests, it helps us to detect muon particles. Inside the muon system, we have an extremely powerful solenoidal magnet. That in turn lends its name to the S of CMS. And it produces a very powerful magnetic field with a strength of 4 Tesla, which is about 100,000 times as powerful as the Earth's magnetic field. Now, the role of this magnet is to bend the trajectory of electrically charged particles emerging through the collisions. And then by carefully measuring the curvature of these trajectories, we can estimate the momentum of these particles. Now, inside the magnet, we have several subdetectors. For instance, we have calorimeters that measure the energy of particles. We also have a silicon sensor-based tracking detector, which helps us to map the trajectory of charged particles. And all of these subdetectors help us to detect, identify, and measure various kinds of particles like hadrons, electrons, photons, and so on. An interesting thing to keep in mind, though, is that if dark matter particles are at all produced in these collisions, we do not expect them to interact with any components of our detector. That is, we expect them to fly off without leaving any trace inside our detector. So then the question is, how do we go about detecting dark matter particles in CMS? Well, I guess this will be discussed more by Deborah in the next discussion.
Can you hear me now? Yes. So thanks, Adish,
yes,
for this tour of CMS. We have indeed your colleague, Deborah Pinna, a physicist from CMS that just arrived, another dark matter hunter. Thank you for joining us, Deborah. And he gave you the hard task of answering the question, if none of the subdetectors of CMS can directly see dark matter particles, then what's the trick?
Yeah, exactly. So I will guide you through that. So for sure, dark matter is one of the biggest puzzles that we have nowadays. And the data that we collect at LHC and that we will collect in the future, they will help us in order to shed light on the nature and the interactions of dark matter. But so you might wonder, how do we actually look for it, for example, in the CMS? So if dark matter is a particle, it might be produced in the collisions that take place at LHC. But we know from the properties inferred from the astrophysical observation that even if we produce dark matter, this will leave the detector without leaving any energy deposit or any visible trace. So this is very challenging, as you can imagine. How can we infer that an invisible particle was produced? So fortunately, we have a solution to that, and that is thanks to how the CMS detector is actually built. So Adish should just show you about the different subdetectors that we have, but the peculiar part is that CMS is being constructed in order to catch, to the extent possible, all the particles, all the visible particles that are produced in the collision. And another tool that we use is the conservation of momentum, which is a fundamental law of physics. And so we know that the momentum that we had before the collision, the ones that we have after the collision, they have to be equal to each other. So it is very important to reconstruct all the visible and standard particles so that we can check if this momentum is actually conserved or apparently not. And in this last case, what happens is that we can infer that an invisible particle, one or more, they were produced in the collision. And another way that you can look at it is like a jigsaw puzzle. And we have a certain picture before the collision. And when the collision takes place, all the pieces of this puzzle, they get scattered around. So our task is going to find all these visible pieces and try to put them together to reconstruct the image that we had before. But sometimes it happens that we don't find some of these pieces, and so we have some holes in this jigsaw puzzle. And in this case, that means that hopefully a dark matter particle was actually produced.
Right, I'm sure this has generated plenty of questions from our viewers, right, Achinthia?
It has indeed. And one of the questions addresses just what you just mentioned, in fact, which is how can these detectors see the subatomic world?
In general.
In general, not just WIMPs, but when you look for, not just dark matter particles, but when you look for them and you talk about missing energy, how are you able to see the other particles? What is the act of seeing for a particle detector?
Yeah, exactly. So as Adish just explained, we have different parts in our detector which they help us in order to distinguish about all the standard particles. So what we have in the standard model and what is stable enough to leave some energy deposits, for example, or to interact with the different part of our subdetectors. Then, of course, we have to put back all this information through softwares and reconstruction in order to know what has passed through, like an electron or a muon or another particle. But so CMS is really built in order to let us know all the different particles, and from that we can reconstruct what happened in the collision.
So you reconstruct from the tracks.
Exactly, exactly. So from these energy deposits, then we just connect them, and then we have the tracks, and then from some properties of this track, we can say, oh, this is an electron, this is a muon, or another particle.
And the key is the material of which CMS subdetectors are made. So when one particle is produced from a collision of the two beams, it crosses these layers, and according to what it's made of, it has a different kind of interaction.
Exactly, exactly. So that helps us distinguish between particles that otherwise, maybe if they have a similar interaction in some part of the detector, then we have another subdetectors which let us know what was really passing through.
So that was the thing that you said earlier about jigsaw puzzles and identification as well. And I jumped the gun a bit when I mentioned the word WIMPs, but this is another question that we have, which is interesting. So what are WIMPs made of? Maybe you could explain to us what WIMPs stand for, what they mean, and how can we use these machines to detect WIMPs?
Okay, so a WIMP stands for a weakly interactive massive particle. So
Which
it's
means
one
it has
of
to have mass.
Exactly,
Okay.
exactly. As to have mass, and of course has also to interact in some way with the standard model component so that we can actually produce it. And so this is what it stands for, and is a dark matter candidate, a possible one. And we like it because in that case, we are able to produce it at colliders and study it in detail. And the way that we detect in case a WIMP is produced in the collision is exactly how I explained. So because like it will interact very weakly, it will just escape the detector, but because we have built CMS in such a way to exploit also this momentum conservation, then we can say, okay, there is the momentum is not conserved, so then that means that we have an invisible particle that passed through, and maybe that is a WIMP.
Achinthia, Adish is still with us, down 100 meters below ground, and he can answer questions as well from down there. There he is.
Hey, Adish. I don't have any specific questions for you about CMS itself, but this maybe you can tell us, expand upon something that we've just heard from Deborah about, which is, so does dark matter have to have mass? Now we know some dark matter candidates do, and the question is, if it does it interfere with particles in different ways than just gravity? So,
right.
This is an interesting question for you.
We do believe that dark matter does have mass. In fact, that is what is required for it to be cold, as was also discussed in the earlier part of our discussion. So yes, we do believe that dark matter should be massive. Then concerning its interactions, in fact, as of now, all that we know about dark matter really comes from its gravitational interactions that we observe astronomically. Now, we do hope that dark matter might also interact with ordinary matter via some very weak interaction. Now, we know that it has to be weak, otherwise we would have seen it already. And this weak interaction could be, as we've also heard before, some new kind of force between dark matter particles and the known matter. And the hope is that in these sort of highly energetic collisions, this kind of force might cause these dark matter particles to emerge from these collisions, and then using the techniques that Deborah explained, although these particles may not interact with any of our detector material, they would create a certain an imbalance in the transverse momentum of the system as a whole, and that would give us a sign of the existence of these particles.
Thanks very much, Adish. We have another question here from Shuvro, and this is probably a question for theorists, but I'm sure you can answer it as well, which is a slightly interesting one in some ways. So often we group the concepts of dark matter and dark energy together when we talk about the stuff that makes up the universe. And is there any relationship between the two?
No, they are very different things. So dark energy is more related to the expansion of the universe. Dark matter really is a form of matter. That's what we believe. In that sense, it's supposed to be very similar, or we expect it to be very similar to ordinary matter because it gravitates. It's just that we do not know how it interacts with ordinary matter, and that's why we call it dark.
Thanks very much. How would you like to proceed, Paula?
Yes, I was just seeing some flashes of light in the center of the detector. I was thinking maybe there are cosmic rays that are colliding. I know it's a stupid question, but it's fun. What do you say, Adish, on that?
Sorry?
We can see every now and then flashes of light right in the center of the detector.
I think these are some lasers.
What are they?
Oh, that's some carbon dioxide interactions, sensors that are producing those flashes there, but unfortunately not cosmic rays.
Yeah, but that leads me to the fact that when you don't have beam, detectors like yours use cosmic rays as well. What do you do in the cosmic run?
Right, so the cosmic rays are actually, they play an extremely important role. They help us in aligning our detectors. Now you see, we are making some extremely precise measurements of the momentum of particles. And for that, as I explained, we have to map the trajectories of charged particles, for instance, and see how they bend in the magnetic field that's produced by this solenoid. Now, to map the trajectory, we need to know very precisely the position of the various active elements of our detector. And you can imagine that's a challenging task, seeing how huge this detector is. And so what we do is to actually use cosmic rays for things like alignment of various subdetectors and so on and so forth.
We now leave you to go to the another big detector around the LHC at the opposite side of CMS. You are in point 5. We are going very soon to point 1 to the Atlas detector. But first, we are going to talk with one of the physicists from Atlas via Skype. Let's take a look at what the Atlas detector looks like first, while we try to connect with our next dark matter hunter, Caterina Doglioni, who is connecting from Ireland. There she is. Hello, Caterina. Can you hear us?
Hello, yes. Can you hear me?
That's great. Thank you for joining us and celebrating together this Dark Matter Day. We've just seen a colleague of yours from the competitor experiment, CMS. We're going to go soon to your cavern, to Atlas, actually not to the cavern, but to the surface area. Both of you are great experiments. You found the Higgs boson back in 2012, and this was a major discovery. Before you started with beams for physics, you were already working in Atlas. Did you expect to find the Higgs boson first, or did you expect to find dark matter first?
Actually, I was hoping to measure the standard model, the things that we know. That's what I was doing at the time. But I think the answer is why not both? Why not finding both dark matter and the Higgs? But I think the Higgs was probably a safer bet than dark matter. And it was expected because we had a lot of clues from the standard model itself that told us where to look for the Higgs. And it's not the same thing for dark matter. We have a lot more possibilities.
And I know you are taking part directly in the searches for dark matter at Atlas. How do you get organized to do that, and how do you do it?
So, as you know, there's a lot of people working on Atlas and CMS. And even though not everyone is involved in the dark matter searches themselves, everyone is indispensable for them. So everyone working on the detector, on the computers, and getting the data out is indispensable for the searches. But in practice, what we look in the data is generally invisible. And I think you've seen it in a number of times before. You've seen it in Suchita's presentation, then you've seen it in. We're looking for what we cannot see, because dark matter does not interact very much with ordinary matter, and our detector is made of ordinary matter. So I don't know if you have a visual behind it.
We are seeing the beautiful Atlas detector.
Okay. Good.
At the moment when it's slightly open, you can see where the beam pipe would go, and you can see some of the octupoles.
Oh yeah, that's beautiful. Yes.
And I think
it's so large that it's
yes.
incredible. If you go down there, you don't realize where the Atlas detector is because it's all over the place.
Yeah. Acinzia has some questions from the viewers for you.
Katerina, thanks for joining us. You mentioned the Higgs boson earlier and how it was, in some ways, a safer bet, an easier thing to find. So Abhishek Sharma has a question for us, which is, does the Higgs boson decay into dark matter?
It's a very good question. And the answer is that we don't know yet, but it's in history the first time that we can test that. So it's really cool that we're looking for this kind of invisible decays of the Higgs boson.
We have another question which comes from Sofia Pessina, which is, what are the main consequences about the existence of dark matter?
Many. I mean, one consequence that you can think about as humans is that we are the minority of the matter. And this is somehow a different way of thinking about yourself, that you're not the center of the world because the universe is made of something different with respect to you. We might be an anomaly. So this is a thought.
There's another question here which has to do with the Higgs boson, but I'm going to slightly rephrase the question for you. Could we have a dark Higgs boson?
Yes, we could. We're also looking for that. We could have multiple dark Higgs bosons. And
another candidate.
You know?
And what would a dark Higgs boson be like? What would its characteristics be, and how would you detect it in Atlas, in a machine like Atlas?
So there are many versions of dark Higgs bosons. So there's some that you could be able to see because it decays into particles, into visible particles. And there could also be dark Higgs boson that decay into invisible particles. So you could take your pick and then see, but we're looking for all of these possibilities. We are leaving no stone unturned. It's really important that we are covering all bases here.
Given its relationship with gravity, rather the way in which we've observed the presence of dark matter in the universe, we have an anonymous question, which is, can we control gravity using dark matter?
Ooh. I think I want to ask this person, can we control dark matter? And then I can answer the second part.
Question to you, can we control dark matter? We haven't seen it, observed it yet, but...
I mean, I think here it's way too early to say what we can do with dark matter, but there is an anecdote that I like mentioning when I get these kind of questions, and that is someone goes to like an important person, that someone from the government goes to a scientist and says, "Oh, good, I've seen you've discovered this electron thing. And what can you do with it? Can you control it?" And the scientist says, well, just think about the time in which you can tax electricity. So there is a big leap of faith between one discovering something and then finding reasons and ways to use it. But it has been done in the past. So first let's discover it and then we think about it. I hope they don't tax dark matter, maybe, I don't know.
So while we have you, we have another question which is also to do with the Higgs boson. So the question itself is from Fuzzle, and the question is, could dark matter interact with the Higgs field? Now, we asked you earlier about whether Higgs bosons can decay into dark matter and whether we can have dark Higgses. But maybe you can tell our viewers a bit about what the Higgs field itself is and its relationship with mass, and given that we're looking for massive particles that we haven't been able to observe, what the relationship is between dark matter and its interaction with the Higgs field itself.
Yeah, so the Higgs field is somehow an all-encompassing thing that exists in nature, and its manifestation is the Higgs boson. So they're very connected between each other. But what the Higgs field does is that it does give mass to particles. So in a way, if you think about the dark matter particles having mass, they need to have a way to interact with some sort of Higgs field in order to get mass. But it doesn't necessarily have to be the standard model Higgs field. It could be something else. And I don't know if this is the answer that you were looking for. I can go into a bit more detail and make similes on how you get mass. But maybe it's too detailed.
I think that would be an entirely different 2-hour-long session on talking about a dark sector Higgs field, which I think is quite fascinating.
Yes, Katarina, I have to thank you for joining us. We know that our mobile crew has in the meantime reached LHC point 1, so we are ready to connect with your colleague Stefan Wilcock, who is waiting for us at one of the surface area of the ATLAS experiment, a place where they are improving one of the major components of the detector is called the muon wheel. So a muon detector that is going to be added to the ATLAS big detector very soon. They are gearing up for a more luminous beam or more luminous beams and collisions in the next run of the LHC in over a year time now, getting ready also for this hunt for dark matter. Do we have ATLAS? We don't have ATLAS yet, so maybe, Acinthia, we can ask some of the theoretical questions to Joachim. I'm sure he has interesting answers to all these combinations of Higgs, dark matter, and gravity, and all these theoretical questions that you got. Maybe you can rephrase one of those.
Let's give it a try. Let's give it a shot. So we have a question here from Mehmet, which is, if we find dark matter and begin to study dark matter, will there be a third mechanical system other than classical and quantum?
Tough.
Most likely not. So when we talk about dark matter, we think that dark matter still obeys the laws of quantum mechanics like everything else in nature. I think discovering an extension of quantum mechanics itself, I think this would maybe be a discovery even more fundamental than the discovery of dark matter.
Wow, all right.
Okay, thank you for filling in this vacuum while we were waiting for the connection with ATLAS, which is now ready. And I see Stefan Wilcock. Thank you, Stefan, for joining the Dark Matter Day at CERN. Can you hear us?
Yes, I can. Can you hear me?
Yes, very loud and clear. And we can see a beautiful piece of detector behind you. What is it that we are seeing, and where are you?
Well, so I can tell you where I am. I am currently in the so-called surface hall, which is the area immediately above the ATLAS cavern where the detector lies, 100 meters below ground. And you probably cannot see, but right behind me, there's a huge shaft, which is about 18 meters wide, through which we can lower and raise the different components of the ATLAS detector. what is right behind me is the so-called small wheel, which is one part of the ATLAS detector that is actually part of the muon spectrometer. I can tell you a little bit more about the ATLAS detector if you like. So the ATLAS detector is really a massive detector that is as tall as about a 6-story building. It's as long as about half the length of a football field. It's composed of many different layers of detecting elements. 6 different types of technologies are being used, going from the innermost components of the detector, which is the so-called pixel detector. It's essentially like a very fancy, large, high-resolution camera. And it is designed to measure the trajectories of charged particles that are produced in these high-energy proton-proton collisions. Then going outwards, there are more tracking detectors that are low-mass detectors that are, again, designed to measure these trajectories of charged particles. Going further outward, we have a couple of calorimeter systems, which are sort of the opposite. They contain very high-density materials and are meant to absorb particles completely so that we can measure their energy. And then the outermost layer of the detector is this muon spectrometer. And the idea behind the ATLAS detector is that we are trying to measure as many of the properties of the particles emitted in proton-proton collisions as possible. So we want to measure their trajectories, their energies, their electric charge, and that will allow us to determine what kind of proton-proton collision takes place. For example, we want to know whether a Higgs boson was produced, or a top quark was produced, or hopefully a dark matter particle was produced. We can only do this with using the detailed information we get from all of these detector elements. And so the small wheel behind me is part of the muon system. There's also a big wheel, which has an area about 10 times larger than the small wheel. So you can get a bit of the sense just how massive the ATLAS detector is.
Wheels in our footage is just amazing. It looks like the small muon wheel, so to say small, is suspended over the shaft. Is it ready to go down?
It actually came out. This is what might be named the old wheel, because we are currently working on an upgrade of that detector element. We are going to hopefully install this new small wheel during this long shutdown before the next running period. And this is really needed in order to be able to cope with the increased collision rate that we anticipate in the next running period, and in the long-term future at the high luminosity Large Hadron Collider, where the collision rate will go even higher, about a factor of 10, and we really need these upgrades to the detector to be able to cope with such high rates.
That's really amazing. I think I'm going to call now everybody else that I asked to go a little bit further so that we could not wear a mask. I'm putting up my mask, and we are ready for the final question and answer questions. We have a lot of dark matter hunters here. We have Stefan in Atlas. We have NA64 represented by Deepan Vita. We have CMS represented by Deborah. We have Michaela for Phaser, and we have Joachim Kopp, our theorist, who can answer everything else that the others cannot answer. So the floor is yours, Cinthia.
I'm going to throw a first question to you, Stefan, over there, which comes to us from Brian. And since you're standing right above the Atlas detector, I thought this was appropriate. How do you protect your instruments from other forms of material, of matter, such as cosmic rays, neutrinos, etc.? How do you shield your detector from these other things that can interfere with your data, your hunt for new particles?
Well, the very fact that the Large Hadron Collider is 100 meters below ground does a very good job shielding our detector from cosmic ray particles. They will get absorbed for the most part, passing through 100 meters of rock and dirt, so that this kind of background is really very small for essentially all of the measurements that we've performed. And on top of that, our precise measurements with the detector really allow us to eliminate if there are any stray muons from cosmic rays. They tend not to go through the collision point where the protons meet. So we can very easily reject those types of muons.
Thanks very much, Stefan. We have a whole lot of other questions. A lot of them are more theoretically motivated, but I will still throw them to all of you. One of the questions which we have is from Gerli in Argentina, which is, will dark matter change its name to something else when we understand what it is and what it does? Well, I suppose it won't change its name, but will we change its name? Who would like to step up and hypothesize about?
Michaela. I can give it a go. So I think dark matter at the moment is a name for what we're calling more of a concept than a real thing. I think most theories predict more than one particle that might be associated with what we're calling these dark sectors, like we talked about dark photons earlier. So I think probably if we discover dark matter, then they will be associated with either new particles, which would have their own names. So we might have, for example, the dark photon, the dark Higgs, and so on. Yeah.
All right.
There are some candidate names already.
Right.
Neutralino, dark photon.
Exactly, yes.
WIMP is also generic.
WIMP is also generic, yeah.
I have another question for our panel, which is from Jemmy. And the question is, what could CERN offer to human civilization with the discovery of dark matter? It's a more profound question and something that we touched upon earlier about things that we discover and their use eventually to society. So does anyone want to take that question? Thank you for being brave.
No, well, I think that we can go back to also what Katerina replied before. First, we need to understand really what it is. We really need to know if we can find it. And then I think that these are all the questions that we can keep aside for now. And then when we know more, then we might be able to answer to that. So I think that are questions that need to wait to have a reply.
Yeah, fair enough. And another question that you touched upon earlier, Joachim, which is to do with black holes. How does dark matter relate to black holes?
Well, the short answer is we don't know. One possibility is that black holes are actually the dark matter. So there's the possibility that what we call dark matter is actually just black holes floating around the universe. As I said earlier in the evening, these black holes that would be the dark matter, these are not the star-eating monsters that you may have seen in movies like the film Interstellar, for instance, but they would probably be much, much smaller than those, maybe about the size of an atom or so. So that's one possibility of many. If dark matter is not made of black holes, of course, dark matter, like every other matter, could still fall into black holes. So it could contribute to the way in which black holes grow. And yet a third possibility is that the very interesting and unusual phenomena that occur close to a black hole could actually help us to search for dark matter. Oh. So one exciting possibility is, for instance, that black holes surround themselves with a fairly dense cloud of dark matter. So there would be a lot of dark matter around black holes, and this might make it easier to detect it. So actually one of the approaches that is being pursued is looking for dark matter in the vicinity of large black holes, like the one at the center of our galaxy.
And
don't forget Stefan is there. Huh?
And another question which we have from Callum, which is also a deeply profound one, I think, which is that if dark matter did not exist, what would our universe look like? Would it affect us in any meaningful way, the way we are, the way we live our lives right now, if dark matter didn't exist in the universe at all? Would you like to take that one?
Yes.
Yeah.
So I think I read this somewhere, and I like this analogy. The dark matter is almost like the scaffolding of our galaxy, which keeps the stars together. So the cluster formation that we see in the universe currently would not exist the way it exists if dark matter doesn't exist. So this will have some implications on the galaxy formation and the stars that we see as well. So yes, it would have an impact.
On a grand scale.
Yes.
But on our day-to-day life.
This is hard to say.
It
would change her life. She would look for something else.
Exactly. There you go.
Yeah.
So it's hard to say.
One for Stefan.
All right, Stefan, I'm going to give you an interesting one because a lot of our questions here are very interesting. Could dark matter be used in the future to make invisible suits or help make things disappear? This is a question from Mriganka.
Yeah,
Do you like science fiction?
Yeah, this sounds like a really cool idea, but perhaps it would be a great idea to write a book. Personally, doubt that we will ever get to that point in terms of using dark matter in any kind of way. So it's dark matter is very weakly. So yeah, the dark matter is very weakly interacting. So I can't imagine that we would be able to manufacture anything with it other than galaxies and large-scale objects.
Thanks very much.
Keep going.
All right, we have a lot of questions.
Shoot.
Is the distribution of dark matter in the universe symmetrical? As far as we know.
So if we look at the observable universe as a whole, it's very, very symmetric. So if we look at all the visible part of the universe as far out as we can possibly see, then on those scales, dark matter is very evenly distributed. If we look in our cosmic neighborhood, for instance, our own galaxy, then it's distributed in a highly non-trivial way. For instance, in those places where there are galaxies or galaxy clusters, there's a lot of dark matter. And between those galaxy clusters, there are huge so-called voids, which are places that are devoid of almost any matter, including dark matter. Now, within a galaxy, if we just look at our own galaxy and ask ourselves, well, how is dark matter distributed within our galaxy? We believe that most likely it's relatively symmetric. So while the visible matter in our galaxy is more disk-shaped, the dark matter halo would be pretty much spherical. Once again, this is a hypothesis that has some observational support, but we are not entirely sure. So there could be asymmetries in the dark matter distribution as well. What we do know for sure is that the dark matter halo of our galaxy has some substructure. So there are still places in it that are denser and less dense. And one of the challenges is to identify those places where it's denser, because where it's denser, we have a larger chance of seeing it. So if, for instance, we use the AMS telescope to look precisely at those places where the dark matter is dense, if that was possible, then we would have a higher chance of seeing it.
While I have you there, I have another question, which is to do with something that you spoke about earlier as well, which is to do with black holes. Now we have been at the LHC searching for micro black holes as a way of looking at extra dimensions, and the question is, what is the relationship between parallel universes, other dimensions, and dark matter? Is there such a strong connection as we sort of hypothesize for gravity and other dimensions?
I would say there is no immediate connection. So the whole idea of parallel universes is a very speculative idea that we have no observational support for. This is very different for dark matter. There's tremendous evidence that there must be some new form of matter in the universe. We don't know what exactly that matter is, but we know it must be there. This is different for the question of parallel universes, for instance.
Thank you for bringing that up, because there was fake news recently about CERN having discovered parallel universe. It's not true. Okay, so from the table of our technical directors are telling us to go a bit faster because we accumulated some delay at the beginning. All these questions, we will distribute them to you guys, and you will be answering directly on the chat on YouTube. We'll tell you how to do that. So now I have to say bye to Stefan. Thank you for showing us a part of Atlas, and thank you for being with us from quite actually opposite where we are now. thanks a lot, and happy Dark Matter Day, and especially a lot of luck to Atlas with the Dark Matter hunt, and also to all the experiments. We are now moving towards the conclusions of our show. We have a final treat, two treats, and maybe some more questions. One treat has to do with art. You know that at CERN there are not just physicists coming, theoretical, experimental, people like me, communicators, but also artists. There is a program of residential artists, and one of them is now in Colombia, and he was here, and he created a work of art inspired by dark matter. So before getting in touch with him, I would like maybe to stay just, we remain just the three of us. You can move a bit further so we can just wait there, and we take off the masks. I would like to see the slide with the Vera Rubin, and we talk a little bit about Vera Rubin with Joachim, because she was actually the inspirer of this work of art. Who was Vera Rubin, Joachim?
So it's fair to say that Vera Rubin is the founder of this field of research. So Vera Rubin was an American astronomer who lived mostly in the 20th century and passed away just 4 years ago, I think, unfortunately. And what Vera Rubin contributed to science was that she did very precise observations of the motion of stars in galaxies. Now, as you may know, the stars that make up a galaxy, they are orbiting around the center of that galaxy. For instance, our own sun is racing around the central part of our Milky Way at a velocity of 240 kilometers per second. So that gives a whole new meaning to the phrase, to live on the fast lane. Everyone on this planet does, because we are moving so fast through our galaxy. But at that speed, the centrifugal force that pushes the sun and our solar system outwards is exactly balanced by the gravitational pull of all the material that's inside the galaxy and pulls the dark matter and pulls the sun towards the center. Now, Vera Rubin observed a lot of stars in a lot of galaxies and asked herself the question, well, is that relation satisfied for them? Does the centrifugal force balance the gravitational pull? And she found that that's not the case. So the stars were moving way too fast for the gravitational pull that she could infer from the material, the amount of matter she saw in those galaxies. So at the speeds at which the dark matter particles were moving, at which the stars were moving, the stars should have been expelled from the galaxies a long, long time ago. Now, they were obviously still there, so there must have been something else that balanced their centrifugal force. And this is how she came to the conclusion that there must be more matter in the galaxies that we can see. And this was really the first very solid piece of evidence of this fact, that there is more matter in the universe that we can see. And so she essentially founded this whole field of research, dark matter.
Thank you, Joachim. I think we have now our artist, Juan Cortez, who is connecting with us from Colombia. There you are. Hi, Juan, and welcome back to CERN. Thank you for celebrating Dark Matter Day with us. So I hope you just heard what Joachim was saying about Vera Rubin, and I'm sure you all know about her story, because she was your inspirer. Tell us, how come that an artist is inspired by an astrophysicist and by a subject like dark matter that is invisible, so it's very difficult to represent with art?
Well, I guess Vera was an enormously important person in this field of research, and for me, I just was so amazed and so impressed by her power of observation, by what she discovered, by she creating this whole field of study that make everyone come together in order to ask themselves about this particularly interesting topic that no one knows exactly what it is, but there you go, and there you have everyone from every nationality, culture, and possible, way trying to measure this and trying to make sense of what this is. So she was very inspiring.
And you created, in her honor, you created this work called Supralunar. Can we see some images of Juan's work of Supralunar, and can you tell us how does it represent dark matter?
Yeah, of course. So I started from some observations of the actual simulations of the morphogenesis of galaxies that scientists at CERN have done in the past. And then with that simulations, with that team of artists called Attractor, and we created this peak this year, and also with a that is like a clock, like a clockwork that simulates the way dark matter supposedly like moving or in this type of matter that moves the stars in the peripheries of galaxies. So it actually creates the whole simulation and has sound also. That's a translation through a transducer of that simulation of the data that scientists created, and then you can experience that through your jaw bones through a bone transducer. So it's like a whole experience to try to take or to make sense, physical sense of what that matter could be actually.
It looks to a CERN experiment, actually, to a physics experiment. It's a work of art, but it looks like a physics experiment, and it's amazing that it can give you an almost physical experience with dark matter by understanding why we know it's there. And it's great that you could use art and contribute to the understanding of science. Do you think this is what the role of art is today?
Probably is one of the roles of art today. I guess right now technology is so important in our culture and in our way of understanding everything, not just the universe or dark matter, by every possible aspect in life. And I really believe that it is our role as artists to think of different ways to use that technology. And I was so inspired by Vera Rubin and by CERN. In the way that they think of technology as a tool to come closer to these philosophic questions or of these fundamental questions, and this is part of something that I know as techno-diversity, and is trying to understand technology in a different way than the one that's currently used in everyday life, right? More closer to like the economic systems and so on and so on. And I find this so important, and the work that you do there is so important in the sense that as an artist, I also wanted to come close to that. Trying to do this understanding of technology.
Much. I hope to see you again at CERN, and I hope you're inspired by more physics and more astrophysics and more mysteries of science, because it's so important to make them become part of everybody's culture, not just those who are passionate for science like our viewers, but everybody. And that's really the strength of art. Thanks a lot.
Thank you very much. Bye.
Okay, so we are now getting closer to the end of our show today. I promised 2 treats. The first one was the artist. And there is another treat that is unexpected. Usually at Halloween, people have tricks and treats. We've seen many tricks. And some treats are edible. So we have an edible treat that has to do with dark matter. Let's show a clip first, and then we'll all taste it, if you agree.
Voila, there's our jelly. So I will cut a triangular shape because that's the closest we can get to dark matter with this. But of course you can cut any shape you want. You can also use a circular shape if you want to play with your jelly lens. Voila. And we will move this bit a bit out of the way. So now it's time to get your laser pointer and your white sheet of paper. And we will also dim the lights a bit to help you see the laser beam going through the jelly. Now focus on the spot of the laser beam on our white sheet of paper. The laser beam represents light from a distant galaxy in this model. So if nothing is in between, you just see that the light goes straight. Now as soon as the laser passes through a weird area of space, in our case the jelly, you will see that the light beam is bent. So now that we finished talking about dark matter, let's come back to the very important question. Can you actually eat this physics experiment? And what about the UV light? We will switch on the UV light to show you. And yes, you can really eat it. Delicious physics.
And yes, indeed, you can eat. You can eat something that has to do with dark matter. You can eat jelly. This was Julia, who is our, she works with the school lab and makes fantastic lessons for teachers and school students with hands-on. And she has prepared some jelly for us. We see in the clip. Would you use this to explain gravitational lensing to somebody who don't know what it is? Maybe before we have our treat, maybe just remind us about gravitational lensing and what has it got to do with jelly?
So gravitational lensing is yet another trick that we can use to look for dark matter. So what gravitational lensing means is looking for the way in which light is distorted by gravity. So like all particles are pulled towards massive objects, and that's also true for light particles. For photons, for the particles that form light. Usually in our everyday lives, that's not a super important effect because the photons that we deal with in everyday life, they have very little energy. So the gravitational pull that they experience is very, very little, especially because they usually travel only relatively short distances. However, if we look at very, very distant objects in the universe, so the light that comes from far, far away in the universe, then the light from there has a long time to get distorted by anything that gravitates along the way. And as we know, most of the things that gravitate along the way is dark matter, because most of the universe is made out of dark matter. And so in fact, this distortion of light from distant stars, that is one way that we can use to search for dark matter. This works best for dark matter objects that are very, very compact. So for instance, if the dark matter is indeed made out of black holes, then this is one of the prime ways of searching for it. And yeah, the analogy to the jelly is that also the jelly distorts the light from, well, this is not a star, this is just a flashlight.
Yes,
but here you can see how passing through the jelly distorts the image of the light on the screen. And that's, in a sense, a visualization of what we're looking for in the universe when we look for gravitational lensing.
And on this, I think we all deserve to taste some of the dark matter. So I welcome you to take your treats. And you also have some more treats, some standard model particle, some dark matter particle. And we say goodbye to everyone who has followed us. The questions that have not been answered live will be answered offline. And thank you very much for viewing. Sorry for the small technical problems. I would like to thank all these dark matter hunters and wish them good luck in their hunt, because we are all going to progress when we advance the frontiers of knowledge. Thank you, everybody, and happy Dark Matter Day.